Hello there. Tonight, we journey beyond the familiar stars into the deepest mysteries of the cosmos. We're going to explore black holes, those enigmatic regions where gravity reigns supreme and the laws of physics dance at their most extreme. Let your breathing slow. Allow your thoughts to settle like cosmic dust drifting through the void. What awaits you is a journey through 100 fascinating truths about these mysterious objects, each fact a gentle step deeper into rest. There's nothing you need to do but listen and let the universe carry you into sleep. Black holes are among the strangest objects in existence, yet they follow rules as precise as any clock. They bend time, swallow light, and reshape the very fabric of space around them. Tonight, we'll discover what they are, how they form, and why they matter to our understanding of everything. So settle in. Let the weight of the day fade away, and prepare to drift through the cosmic dark, guided by the quiet pull of gravity itself. Imagine a place where the pull of gravity becomes absolute, where every particle, every wave of energy, every photon of light that ventures too close finds itself trapped forever. This is what defines a black hole. The force that holds planets in orbit, that keeps our feet on the ground, becomes so overwhelming in these regions that escape is impossible. Even traveling at the speed of light, the fastest velocity in the universe, wouldn't be enough to break free once you've crossed a certain boundary. That boundary, that point of no return, marks the edge of something truly extraordinary. For centuries, thinkers wondered about objects whose gravity might be strong enough to trap light. In the 1700s, both John Michel and Pierre-Simon Laplace pondered such possibilities, imagining what they called dark stars. But the modern understanding began with Albert Einstein's general theory of relativity in 1915. It was physicist John Wheeler who in 1967 coined the phrase black hole during a lecture. The name stuck because it captured perfectly what these objects are: holes in the visible universe, utterly black because no light emerges from them. Stars are born in clouds of gas and dust, ignite through nuclear fusion, and shine steadily for millions or billions of years. But eventually, even the mightiest stars exhaust their fuel. When a star at least 8 to 10 times more massive than our Sun reaches this point, its core can no longer support itself against gravity's relentless inward crush. The core collapses in a fraction of a second, compressing matter to densities beyond imagination. If the remaining core after this collapse exceeds about 3 solar masses, nothing can stop the implosion. The result is a stellar mass black hole, born from the death of a giant. The event horizon is not a physical surface like the ground beneath your feet. It's an invisible threshold, a point in space beyond which the gravitational pull becomes inescapable. Cross this line and you've entered a region from which no information, no signal, no particle can ever return to the outside universe. It marks the beginning of a one-way journey into the unknown. The event horizon is perfectly smooth and spherical, if the black hole isn't spinning. Its size depends entirely on the black hole's mass. For a black hole 10 times the mass of the Sun, the event horizon has a radius of about 30 kilometers. Small by cosmic standards, yet within it lies an infinite mystery. If the event horizon is the doorway, the singularity is the destination. According to general relativity, all the mass of the black hole is crushed down into a single point of zero volume and infinite density. At this singularity, the known laws of physics break down completely. Space and time lose their meaning. Gravity becomes infinite. No one knows what truly exists at this point because our current theories cannot describe it. The singularity represents the limit of human understanding, a place where the universe guards its deepest secrets. Light is the fastest thing in existence, racing through space at nearly 300,000 kilometers per second. Yet even this incredible speed is insufficient to overcome the gravitational well inside a black hole's event horizon. Photons that cross this boundary are bent inward so severely that all paths lead only deeper into the black hole. They spiral down toward the singularity, never to emerge. This is why black holes appear completely black. They emit no light of their own and allow none to escape. The darkness of a black hole is absolute and eternal. Since black holes emit no light, astronomers must look for their influence on surroundings. When a black hole pulls gas from a nearby companion star, that gas forms a swirling disk around the black hole. Friction heats this disk to millions of degrees, causing it to glow brilliantly in X-rays. These X-ray emissions can be detected by space telescopes, revealing the presence of the invisible object at the center. Scientists also watch for stars whose motion suggests they're orbiting something massive yet unseen. Through these indirect methods, astronomers have identified hundreds of black holes scattered throughout our galaxy and beyond. Stellar mass black holes form from collapsed stars and typically weigh between 5 and 100 times the mass of our Sun. They're scattered throughout galaxies, remnants of massive stars that died long ago. Intermediate mass black holes range from roughly 100 to 100,000 solar masses. These are rarer and harder to detect, possibly forming in dense star clusters or through the merger of smaller black holes. Supermassive black holes are the giants, containing millions to billions of solar masses. They lurk at the centers of most galaxies, including our own Milky Way. Each type tells a different story about how black holes grow and shape the cosmos around them. In cosmic terms, 1,500 light-years is practically next door. This black hole, called Gaia BH1, was discovered by studying the motion of its companion star. The star wobbles in its orbit, tugged by the invisible gravitational pull of the black hole beside it. Though this black hole is our closest known neighbor of its kind, there's no need for concern. At such a distance, it has absolutely no effect on Earth or our solar system. The nearest black holes are simply part of the cosmic landscape, distant waypoints in the vast sea of stars that surrounds us. Deep in the heart of our galaxy, hidden behind vast clouds of dust and gas, sits a monster, Sagittarius A star, often written as SGAR, a star, contains the mass of over 4 million suns compressed into a region smaller than Mercury's orbit. Astronomers discovered it by tracking the orbits of stars near the galactic center. These stars move at incredible speeds, whipping around an invisible point in elliptical paths that betray the presence of something immensely massive. In 2022, the Event Horizon Telescope captured the first image of Sagittarius A star's shadow, providing direct visual evidence of this cosmic giant that anchors our galaxy. The range of black hole masses is staggering. A stellar black hole might weigh 10 suns, compact enough to fit within a small city. But supermassive black holes are entities of an entirely different scale. The black hole at the center of the galaxy M87 weighs 6.5 billion times as much as our Sun. Its event horizon spans a diameter of about 40 billion kilometers. If you could somehow stand near it, the black hole would fill your entire field of view, a vast darkness ringed by the warped light of the universe bending around it. These cosmic behemoths shape the evolution of entire galaxies through their gravitational influence. In the constellation Canis Venatici, more than 10 billion light-years away, lies TON 618. This ultra-massive black hole tips the scales at 66 billion solar masses, making it one of the most massive objects ever detected. Its event horizon would encompass a region larger than our entire solar system many times over. TON 618 sits at the center of a quasar, one of the brightest objects in the universe, powered by gas falling into the black hole at an extraordinary rate. The sheer scale of such an object challenges our understanding of how black holes can grow so large in the age of the universe. Just as Earth spins on its axis, black holes can rotate. When a massive star collapses, it carries its angular momentum into the black hole it becomes. Some black holes spin at incredible rates. The fastest known, designated GRS 1915 + 105, completes over 1,000 rotations each second. This spinning creates a phenomenon called frame dragging, where the black hole literally drags space-time around with it, like water swirling down a drain. Near a rapidly spinning black hole, space itself is forced to move in the direction of rotation, adding another layer of complexity to an already mind-bending environment. One of the strangest predictions of general relativity is gravitational time dilation. The stronger the gravitational field, the slower time passes relative to regions with weaker gravity. Near a black hole's event horizon, this effect becomes extreme. If you could hover just outside the event horizon and watch the distant universe, you would see time passing rapidly. Stars would age and die in what seemed like moments. But to observers far away, you would appear nearly frozen, your movements slowed to a crawl. At the event horizon itself, time from an outside perspective would appear to stop completely. This warping of time is not an illusion. It's a fundamental consequence of how gravity shapes the fabric of space-time. This has a rather whimsical name for a deeply unsettling process. As you approach a black hole feet first, the gravitational pull on your feet would be significantly stronger than the pull on your head due to the difference in distance from the singularity. This difference in gravitational force, called a tidal force, would stretch you vertically while compressing you horizontally. The stretching would intensify as you fell closer, eventually pulling you into a long, thin shape resembling a strand of spaghetti. For stellar mass black holes with smaller event horizons, spaghettification would begin before you even reached the event horizon, tearing you apart atom by atom. For supermassive black holes with their larger, gentler event horizons, you might pass through relatively intact before meeting your end deeper within. A common misconception is that black holes act like cosmic vacuum cleaners, pulling in everything around them. In reality, a black hole's gravitational influence follows the same rules as any other massive object. If you replaced the Sun with a black hole of equal mass, Earth would continue orbiting exactly as it does now. It wouldn't be sucked in. You only get pulled into a black hole if you venture too close to the event horizon, or if you're moving slowly enough that your trajectory intersects it. At safe distances, objects can orbit black holes stably, just as planets orbit stars. The danger lies in proximity and the extreme conditions near the event horizon, not in some supernatural suction force. Cygnus X1 is a stellar mass black hole in a binary system with a blue supergiant star. The black hole pulls material from its companion, forming an accretion disk that glows intensely in X-rays. When astronomers detected these X-rays in 1964, they weren't initially sure what caused them. By 1971, studies of the system revealed that the compact object had to be too massive to be a neutron star, meaning it could only be a black hole. This discovery marked a turning point, transforming black holes from theoretical curiosities into confirmed astronomical objects. The evidence was so compelling that even physicist Stephen Hawking, who had famously bet against the existence of Cygnus X1 as a black hole, conceded defeat. As astronomers have surveyed galaxies across the universe, a pattern has emerged. Nearly every large galaxy appears to harbor a supermassive black hole at its core. The relationship between galaxy and black hole runs deep. The mass of the central black hole correlates with properties of the galaxy itself, such as the motion of stars in its bulge. This suggests that galaxies and their central black holes grow together, influencing each other's evolution. The supermassive black holes aren't simply passengers. They play an active role in regulating star formation and shaping the structure of their host galaxies through powerful outflows and jets. On April 10, 2019, scientists unveiled an image that captured worldwide attention and marked a milestone in astronomical history. The first photograph of a black hole's shadow. The target was M87 star, the supermassive black hole at the center of the galaxy Messier 87, located 55 million light-years away. The image showed a bright ring of glowing gas surrounding a dark central shadow, exactly as predicted by Einstein's theory of general relativity over a century earlier. To achieve this extraordinary feat, astronomers synchronized 8 radio telescopes around the world, from Hawaii to the South Pole to Spain, creating a virtual telescope the size of Earth itself. The data collected during just a few nights of observation filled hundreds of hard drives, and had to be physically shipped to processing centers because it exceeded what could be transferred over the internet. Processing it required sophisticated algorithms, supercomputers, and years of painstaking work by hundreds of scientists. The result was worth every moment of effort: direct visual evidence of one of the universe's most extreme phenomena, confirming predictions and opening a new era of black hole imaging. Following their success with M87 Star, the Event Horizon Telescope team turned their attention closer to home. Imaging Sagittarius A star proved more challenging despite its proximity. While M87 Star is thousands of times more massive and therefore larger, making it a steadier target, Sagittarius A star is much smaller, and the gas around it changes on timescales of minutes. As one member of the team described it, it was like trying to photograph a puppy chasing its tail. The team developed new techniques to account for this variability, essentially averaging multiple rapid snapshots to create a stable image. The final picture, released in May 2022, showed a structure remarkably similar to M87 Star, a bright ring with a dark central shadow, confirming that our galactic center indeed hosts a supermassive black hole. In 1974, Stephen Hawking made a startling discovery. He calculated that black holes aren't completely black after all. Quantum effects near the event horizon allow black holes to emit a faint thermal radiation, now called Hawking radiation. This radiation arises from the properties of quantum fields in the curved space-time around the black hole. The temperature of this radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the temperature is incredibly tiny, far colder than the cosmic microwave background that permeates space. For supermassive black holes, it's even lower. Though Hawking radiation has never been directly observed due to its extreme faintness, its theoretical prediction has profound implications for black hole physics and quantum gravity. Because black holes emit Hawking radiation, they gradually lose mass and energy. This process is extraordinarily slow. A solar mass black hole would take about 10 to the 67th power years to evaporate completely, vastly longer than the current age of the universe. Supermassive black holes would persist even longer. As a black hole loses mass, its temperature increases, causing it to radiate faster and lose mass more quickly. Eventually, in the final moments of its existence, a black hole would evaporate in a burst of radiation. This means that black holes, despite their reputation as eternal prisons, have finite lifespans, though those lifespans are almost inconceivably long. Quantum mechanics tells us that information cannot be destroyed. But if something falls into a black hole and the black hole later evaporates through Hawking radiation, where does the information go? Does it disappear forever, violating quantum principles? Or is it somehow encoded in the radiation? This puzzle, known as the black hole information paradox, has troubled physicists for decades. Recent work suggests that information might indeed be preserved in subtle correlations in the Hawking radiation, but the exact mechanism remains debated. Resolving this paradox may require a complete theory of quantum gravity, unifying general relativity and quantum mechanics in ways we don't yet fully understand. When two black holes orbit each other, they gradually spiral inward, releasing energy in the form of gravitational waves. These waves are literally ripples in the fabric of space-time itself, traveling outward at the speed of light. As the black holes draw closer, they orbit faster and emit stronger waves. Finally, they collide and merge in a violent event lasting fractions of a second. The merger produces a new, larger black hole and releases tremendous energy as gravitational waves. These waves carry information about the masses and spins of the merging black holes, encoded in the pattern of the signal as it sweeps upward in frequency, creating what scientists call a chirp. On September the 14th, 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, or LIGO, simultaneously registered a signal that changed astronomy. The signal, designated GW5914, was produced by the merger of two black holes approximately 36 and 29 times the mass of the Sun, located over 1 billion light-years away. The gravitational waves stretched and squeezed space as they passed through Earth, changing the distance between LIGO's mirrors by a tiny fraction of the width of a proton. This detection confirmed a prediction Einstein made a century earlier and opened an entirely new way to observe the universe. The leaders of LIGO received the Nobel Prize in Physics in 2017 for this groundbreaking discovery. Following that first detection, gravitational wave astronomy has flourished into a new field of observational science. LIGO, joined by the Virgo detector in Italy and Kagra in Japan, has observed hundreds of merger events, fundamentally changing how we study the universe. Most involve pairs of black holes, but some are mergers of neutron stars, or a black hole with a neutron star. Each detection provides insights into the population of compact objects in the universe, how they form, and how they evolve over cosmic time. The most massive merger detected so far, called GW231123, involved black holes of about 100 and 140 solar masses, producing a final black hole of 225 solar masses. These observations continue to test general relativity in extreme conditions where gravity is strongest, and they reveal phenomena that were pure theory just a decade ago. Every new detection adds to our understanding of how black holes populate the cosmos and how they interact. Not all stars can become black holes. Stars with masses less than about 8 times the Sun's mass will end their lives as white dwarfs or neutron stars. But stars more massive than this threshold can produce black holes. When such a star exhausts its nuclear fuel, its core collapses catastrophically. If the core's mass exceeds roughly 3 solar masses, the collapse continues past even the density of a neutron star. Nothing can halt the implosion, and a black hole forms. The outer layers of the star may be blown away in a supernova explosion, leaving the black hole behind. The more massive the original star, the more massive the resulting black hole tends to be. In the first moments after the Big Bang, the universe was extraordinarily dense and hot. Theorists have proposed that fluctuations in density during this early era could have caused some regions to collapse directly into black holes, called primordial black holes. Unlike stellar black holes, which require the death of a massive star, primordial black holes could theoretically have formed with a wide range of masses, from tiny microscopic black holes to massive ones. If they exist, these ancient black holes have been wandering the universe since the beginning of time. Based on Hawking's calculations, small primordial black holes would have evaporated by now through Hawking radiation. Larger ones might contribute to the mysterious dark matter that makes up much of the universe's mass, though this possibility remains unconfirmed. At extremely small scales, quantum effects become important. The Planck mass, about 22 micrograms, represents the scale where quantum mechanics and gravity become equally significant. A black hole with this mass would have an event horizon smaller than the Planck length, the smallest meaningful distance in physics. At such scales, our current theories break down. Quantum fluctuations would dominate, and the black hole would evaporate almost instantaneously through Hawking radiation. While such tiny black holes might have formed in the early universe, or could theoretically be created in high-energy particle collisions, none have ever been detected. They remain purely hypothetical, existing at the very edge of what physics can describe. Many stars exist in binary systems, orbiting a common center of mass with a companion. When one member of a binary is a black hole, the system can produce spectacular effects. If the companion star is close enough, the black hole's gravity pulls material from the star's outer layers. This material doesn't fall straight in. Instead, it forms a flattened accretion disk spiraling around the black hole. Friction within the disk heats the gas to millions of degrees, causing it to emit intense X-rays. Many known black holes have been discovered through these X-ray signatures. The material spiraling inward reaches extreme speeds, sometimes exceeding a significant fraction of light speed before crossing the event horizon. When matter falls toward a black hole, it doesn't simply plunge straight in. Conservation of angular momentum forces the material into orbit, forming a disk. Within this disk, particles collide and interact, transferring energy through friction. This process heats the disk to extreme temperatures. In the innermost regions, temperatures can exceed 10 million degrees Kelvin. At such temperatures, the gas becomes a plasma, emitting X-rays and gamma rays. The hottest regions are closest to the black hole, where orbital velocities approach the speed of light and the density of material is highest. These accretion disks are some of the most energetic environments in the universe, converting gravitational potential energy into radiation with remarkable efficiency. In about 10% of cases, black holes produce narrow beams of particles and radiation that shoot outward from near the poles at nearly the speed of light. These jets can extend for thousands or even millions of light years, far beyond the galaxy hosting the black hole. The mechanism behind jet formation involves the black hole's spin and powerful magnetic fields threading through the accretion disk. As the disk rotates, it twists magnetic field lines, which channels some of the infalling material outward along the rotation axis. The particles in these jets are accelerated to relativistic speeds, creating beams of incredible power that can significantly affect the evolution of their host galaxies and the intergalactic medium around them. Quasars are among the brightest objects in the universe, outshining entire galaxies despite being no larger than our solar system. These extreme sources are powered by supermassive black holes actively feeding on surrounding gas and dust. Material falls into the black hole at rates equivalent to consuming hundreds or even thousands of Earth masses every year. The intense radiation from the hot accretion disk can exceed the energy output of trillions of stars. Quasars were more common in the early universe when galaxies were forming and gas was more abundant, reaching peak numbers when the universe was just a few billion years old. Observing distant quasars allows astronomers to study conditions billions of years in the past, providing a window into the universe's history. The light from these objects has traveled for so long that we're seeing them as they existed when the cosmos was still young and galaxies were actively assembling. When a supermassive black hole at a galaxy's center is actively feeding, it creates what's called an active galactic nucleus, or AGN. The classification includes quasars, blazars, and Seyfert galaxies, differentiated mainly by their orientation relative to Earth and the specific characteristics of their emissions. All AGN share common features: a supermassive black hole, an accretion disk of infalling matter, and often a dusty torus surrounding the inner regions. The tremendous energy released by the accreting material makes AGN visible across vast cosmic distances. Studying AGN helps astronomers understand how supermassive black holes grow and how they influence the galaxies that host them. When one of the relativistic jets from an AGN happens to be aimed almost directly at Earth, we see what astronomers call a blazar. Relativistic beaming causes the jet's radiation to be amplified and concentrated in the forward direction, making the blazar appear extraordinarily bright. The light from blazars can vary dramatically over short periods, sometimes changing in brightness by factors of 2 or more in a single day. These variations reflect changes in the jet itself as material within it moves and interacts. Blazars produce radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, making them fascinating laboratories for studying extreme physics and particle acceleration. Astronomers have discovered a tight relationship between the mass of a galaxy's central supermassive black hole and properties of the galaxy itself. Specifically, the black hole's mass correlates with the velocity dispersion of stars in the galactic bulge, a relationship known as the M-sigma relation. This suggests that galaxies and their black holes don't evolve independently. Instead, they influence each other through feedback processes. Jets and winds from the active black hole can heat gas throughout the galaxy, regulating star formation. Conversely, galaxy mergers funnel gas toward the center, feeding the black hole and allowing it to grow. This cosmic symbiosis shapes the structure and evolution of galaxies across cosmic time. German physicist Karl Schwarzschild derived the first exact solution to Einstein's equations of general relativity in 1916, just months after Einstein published his theory. The solution describes the space-time geometry around a spherical, non-rotating mass. The Schwarzschild radius is the distance from the center at which the escape velocity equals the speed of light. For any object compressed within its Schwarzschild radius, it becomes a black hole. This critical radius is directly proportional to the mass. For the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it's roughly 9 millimeters. Of course, neither object is actually a black hole because their matter extends far beyond these tiny radii. Only when matter is compressed within this boundary does a black hole form. As you move closer to a black hole, the orbital velocity required to remain in a circular path increases. Eventually, you reach a point where no stable orbit exists. This boundary is called the innermost stable circular orbit, or ISCO. For a non-rotating black hole, the ISCO is located at 3 times the Schwarzschild radius, or 6 kilometers for a solar mass black hole. Inside this radius, matter inexorably spirals inward, crossing the event horizon. The ISCO's location depends on the black hole's spin. For rapidly rotating black holes, it can be closer to the event horizon. Most of the energy released from an accretion disk comes from material in the region just outside the ISCO, where orbital velocities are highest and heating is most intense. While Schwarzschild solved Einstein's equations for a non-rotating black hole, the mathematics for a spinning black hole proved far more complex. In 1963, New Zealand mathematician Roy Kerr found the solution. The Kerr metric describes space-time around a rotating black hole and reveals fascinating features. Rotation causes the black hole's event horizon to bulge at the equator. It also creates a region outside the event horizon called the ergosphere, where space-time itself is dragged around by the black hole's spin. The structure of rotating black holes is richer and more complex than their non-rotating counterparts. Yet remarkably, the solution depends only on 2 parameters: mass and spin. In the ergosphere, the rotation of the black hole drags space-time along with it, a phenomenon called frame dragging. Within this region, it's impossible to remain stationary. Everything must rotate in the same direction as the black hole. However, unlike the interior of the event horizon, escape from the ergosphere is still possible. In principle, particles or light can enter the ergosphere, interact with the intense gravitational field, and emerge with more energy than they entered with, extracting rotational energy from the black hole. This process, known as the Penrose mechanism after physicist Roger Penrose, could theoretically provide a way to harvest energy from rotating black holes, though no practical implementation exists. The complete solution to Einstein's equations for a charged rotating black hole is called the Kerr-Newman metric. It describes a black hole characterized by 3 properties: mass, spin, and electric charge. However, astrophysical black holes are expected to be essentially neutral. Any net charge would quickly be neutralized by attracting oppositely charged particles from the surrounding environment. Even if a black hole briefly acquired a charge, the electromagnetic force would dominate over gravity, and the charge would be rapidly dissipated. For this reason, the electric charge parameter is usually assumed to be negligible in real black holes, and the Kerr metric for uncharged rotating black holes is sufficient to describe them. According to the no-hair theorem, black holes are remarkably simple objects. Once formed, a black hole sheds all information about the matter that created it, except for 3 properties: its mass, its angular momentum or spin, and its electric charge. All other details, such as the composition of the original star, its temperature, its magnetic field, are lost. This simplicity is striking given the complexity of astrophysical objects. The theorem implies that very different initial states can produce identical black holes. While exceptions and complications exist in more advanced theories, the basic principle holds. Black holes are defined by just a handful of numbers, making them among the simplest macroscopic objects in nature. Black hole thermodynamics, developed in the 1970s by physicists including Jacob Bekenstein and Stephen Hawking, reveals deep connections between gravity, quantum mechanics, and thermodynamics. A black hole has a temperature inversely proportional to its mass, defined by the Hawking temperature. For stellar mass black holes, this temperature is incredibly low, far below the temperature of the cosmic microwave background. As a black hole radiates and loses mass through Hawking radiation, its temperature increases. The smallest black holes would be the hottest, though still unimaginably tiny. This temperature is not just an analogy. It represents real thermal radiation that the black hole emits, albeit undetectably faint for astrophysical black holes. In thermodynamics, entropy measures disorder or the number of possible microscopic states of a system. Bekenstein proposed that black holes have entropy, and Hawking showed it's proportional to the area of the event horizon, not the volume. This is remarkable because for ordinary objects, entropy typically scales with volume. The formula is elegant. The entropy equals 1/4 of the event horizon's area measured in Planck units. This result suggests that the information content of a black hole is somehow encoded on its two-dimensional surface, rather than throughout its three-dimensional interior. This idea has inspired holographic principles in theoretical physics, suggesting that the information content of a region of space might be encoded on its boundary. Between stellar mass black holes and supermassive ones lies a mysterious middle ground. Intermediate mass black holes, with masses from hundreds to hundreds of thousands of solar masses, are harder to find than their smaller or larger cousins. Scientists propose several possible formation scenarios, though none are yet confirmed. They might form through runaway collisions in dense star clusters, where stars repeatedly merge until they create a massive star that collapses. Another possibility involves the direct collapse of massive gas clouds in the early universe. Evidence suggesting intermediate mass black holes has been found in globular clusters and dwarf galaxies, but confirmed detections remain rare. Understanding how these black holes form and grow could help explain how supermassive black holes achieved their enormous masses. Mass warps space-time, causing light to follow curved paths. A massive object like a black hole can act as a gravitational lens, bending the light from more distant sources. If a black hole passes between Earth's and a background star, the star's light is deflected, potentially creating multiple distorted images or a brightening event. This microlensing effect has been used to detect isolated black holes that would otherwise be invisible. Strong gravitational lensing near black holes creates dramatic effects. Light can orbit the black hole multiple times before escaping, creating rings and arcs of light. The shadow seen in images of M87 star and Sagittarius A star is surrounded by such a photon ring, where light has been bent around the black hole. Gravitational time dilation is one of the most counterintuitive predictions of relativity. To an outside observer, a clock near a black hole's event horizon would appear to tick ever more slowly as it approaches the horizon. At the horizon itself, time appears to stop completely from the outside perspective. This isn't an illusion. Time genuinely passes at different rates in different gravitational fields. An astronaut hovering near the event horizon would age more slowly than someone far from the black hole. This effect was dramatized in the film Interstellar, where characters on a planet orbiting close to a massive black hole experienced extreme time dilation, with hours for them corresponding to years for distant observers. General relativity describes gravity as the curvature of space-time caused by mass and energy. Near a black hole, this curvature becomes extreme. Space is warped to such a degree that within the event horizon, all possible paths lead inward toward the singularity. Even light, which always travels in straight lines through space-time, finds that every straight path leads only deeper into the black hole. Outside the event horizon, outward paths still exist, but crossing that boundary means entering a region where the future inevitably points inward. The event horizon represents a geometric point of no return, a place where the structure of space-time itself prevents escape. When two black holes orbit each other, their dance generates gravitational waves that carry energy away from the system. As the binary loses energy, the black holes spiral closer together, orbiting faster and emitting stronger waves. This process can continue for millions or billions of years if the black holes start far apart. But eventually, they enter a phase where the in-spiral accelerates dramatically. In the final moments, the black holes circle each other hundreds of times per second, sweeping through space at a significant fraction of light speed. The gravitational waves from this in-spiral chirp upward in frequency until the black holes merge in a violent collision that releases more energy in gravitational waves than all the stars in the observable universe emit as light. When black holes merge, the energy released is staggering beyond ordinary comprehension. In the first detected merger, GW150914, the final black hole had a mass of 62 solar masses, but the two original black holes together had 65 solar masses. The missing 3 solar masses worth of energy, an amount equal to the mass of 3 entire suns, was radiated away as gravitational waves in a fraction of a second. Using Einstein's famous equation E equals mc squared, that's roughly 5.4 times 10 to the 47th joules of energy, more than the sun will emit in light over its entire 10 billion year lifetime, all released in less than a second. This energy doesn't involve nuclear reactions or chemical processes. It's pure gravitational energy, released through the violent restructuring of space-time itself as two black holes become one. The peak power output during the merger exceeded the combined light output of all stars in the observable universe at that instant. For that brief moment, this single event was the most luminous occurrence in the cosmos, though invisible in light and detectable only through the ripples it sent through space-time itself. Not all gravitational wave detections involve black hole pairs. In some cases, a neutron star and black hole orbit each other and eventually merge. The first confirmed detections of such mergers came in 2020, when LIGO and Virgo observed two events within 10 days. These mergers produce gravitational wave signals slightly different from black hole. Black hole mergers due to the different masses involved. If the neutron star survives long enough to reach the black hole's tidal forces intact, can be torn apart before being swallowed, potentially producing additional electromagnetic signals. Studying these hybrid mergers helps astronomers understand the population of compact objects and the extreme physics governing them. Dark matter makes up about 85% of the matter in the universe, yet its nature remains unknown. One intriguing possibility is that some fraction of dark matter could consist of primordial black holes formed in the early universe. These ancient black holes would not emit light, making them consistent with dark matter's invisibility. Searchers for primordial black holes use gravitational microlensing, looking for the telltale brightening of stars when a black hole passes in front. So far, these searchers have ruled out primordial black holes as the dominant component of dark matter over most mass ranges. But small windows remain where they could potentially contribute. The question of whether primordial black holes exist and what role they might play in the cosmic matter budget remains an open area of research. Globular clusters are ancient, dense collections of stars orbiting galaxies. With thousands of stars packed into a small volume, interactions are frequent. Based on dynamical models, intermediate mass black holes might form in these clusters through stellar collisions and mergers. But the same dynamical interactions that create them can also eject them from the cluster through gravitational slingshot effects. Alternatively, multiple black holes might sink to the cluster center, forming binaries that eventually merge and generate gravitational waves. Recent observations have found evidence suggesting intermediate mass black holes lurking in some globular clusters, detected through their gravitational influence on nearby stars. These findings provide clues about black hole formation in dense stellar environments, though much remains to be understood. In 1783, English natural philosopher John Michell speculated about dark stars with gravity strong enough to prevent light from escaping. He calculated that a star with the Sun's density but 500 times its diameter would have an escape velocity exceeding the speed of light. Pierre-Simon Laplace independently proposed similar ideas in 1796. Of course, neither Michel nor Laplace understood the relativistic nature of gravity or the strange properties that modern black holes possess. Their Newtonian dark stars were conceptual precursors, intriguing but incomplete. The true understanding of black holes required Einstein's general relativity, which revealed that space-time itself is curved by mass, leading to phenomena far stranger than simple dark stars. Despite deriving the field equations that predict black holes, Einstein struggled with their implications. In 1939, he published a paper arguing that singularities could not actually form because matter would need to exceed the speed of light to collapse to infinite density. He believed that some unknown mechanism would prevent the formation of such extreme objects. History proved Einstein wrong. Later work by physicists including Oppenheimer, Snyder, Wheeler, and Penrose showed that gravitational collapse could indeed produce black holes under realistic conditions. Once again, the universe turned out to be stranger than even Einstein imagined. Black holes transitioned from mathematical curiosities to accepted astrophysical objects, despite their discoverers' doubts. In 1965, Roger Penrose made groundbreaking contributions to the theory of black holes. He proved that once an event horizon forms, the collapse to a singularity is inevitable, given certain reasonable assumptions. Before Penrose's work, it was thought that singularities might be mathematical artifacts that wouldn't occur in realistic situations. His singularity theorems showed that singularities are generic features of gravitational collapse, not special cases. This work laid the foundation for modern black hole physics. In 2020, Penrose was awarded the Nobel Prize in Physics for discovering that black hole formation is a robust prediction of general relativity. He shared the prize with Reinhard Genzel and Andrea Ghez, who were honored for discovering the supermassive black hole at the Milky Way's center. For decades, astronomers tracked the motions of stars near the center of the Milky Way with extraordinary dedication and precision. Genzel, Ghez, and their teams independently followed these stars with remarkable precision, using some of the world's most powerful telescopes, including the Very Large Telescope in Chile and the Keck Observatory in Hawaii. They found that stars orbit an invisible object at extraordinary speeds, following elliptical paths that could only be explained by something incredibly massive at the center. One star, called S2, completes an orbit in just 16 years, reaching speeds up to 3% of light speed as it whips around this invisible point. The orbital data from this star and others allowed precise measurements of the central mass, over 4 million solar masses, concentrated in a region no larger than our solar system. These observations provided the strongest evidence for a supermassive black hole at the galactic center, confirming decades of theoretical predictions and ruling out alternative explanations. For this groundbreaking work spanning more than 25 years of careful observations, Genzel and Ghez shared the 2020 Nobel Prize in Physics. When a star wanders too close to a supermassive black hole, especially if the black hole is part of a binary system, the gravitational interaction can fling the star outward at tremendous speed. These hypervelocity stars can be ejected from their host galaxies entirely, traveling through intergalactic space at velocities exceeding the galaxy's escape velocity. Astronomers have discovered several such stars speeding through the Milky Way. By tracing their trajectories backward, these stars appear to originate from the galactic center. The existence of hypervelocity stars provides evidence for the extreme gravitational dynamics near pure supermassive black holes and the possibility of binary supermassive black holes at galactic centers. A star approaching a supermassive black hole can be torn apart by tidal forces if it crosses within a certain distance, called the tidal disruption radius. The difference in gravitational pull between the star's near and far sides exceeds the star's own gravity, ripping it to shreds. The stellar debris forms a luminous accretion stream that partially falls into the black hole and partially escapes. These tidal disruption events produce bright flares of radiation that can outshine their entire host galaxy for weeks or months. Astronomers have observed dozens of these events, providing insights into the population of otherwise quiet supermassive black holes. Each flare offers a rare glimpse of a black hole suddenly awakening to feed on fresh material. When matter falls into a black hole, it might seem to disappear from the universe. But the mass and energy are not destroyed. They're added to the black hole. The black hole's mass increases by exactly the amount that fell in, preserving the conservation of energy. Similarly, angular momentum and electric charge are conserved. If matter with spin falls into a black hole, the black hole's spin changes accordingly. These conservation laws remain inviolate even in the extreme environment of a black hole. The matter's detailed structure may be lost, reduced to just mass, spin, and charge, as per the no-hair theorem, but the fundamental conserved quantities endure, incorporated into the black hole's own properties. In the universe's first moments, density fluctuations could have been extreme enough for regions to collapse directly into black holes without needing stellar evolution. These primordial black holes could range from microscopic to many solar masses. Unlike stellar black holes, which cannot be smaller than a few solar masses, primordial black holes could have formed with any mass. Tiny ones would have evaporated long ago through Hawking radiation. Intermediate mass primordial black holes might still exist, hiding in the cosmos. If detected, they would provide a unique window into the early universe's conditions. Searchers continue using gravitational waves, microlensing, and other techniques, seeking evidence of these ancient relics from the dawn of time. Carl Schwarzschild's solution to Einstein's equations, found while serving in the German army during World War I, remains one of the most important exact solutions in general relativity. It describes the space-time geometry around any spherically symmetric mass. For a black hole, the metric reveals a singularity at the center and an event horizon at the Schwarzschild radius. The solution is remarkably elegant, depending only on the mass parameter. It predicts phenomena like gravitational time dilation, light bending, and the existence of photon spheres where light can orbit the black hole. Despite being over a century old, the Schwarzschild metric continues to be the starting point for understanding black holes and testing general relativity. Many of the known stellar mass black holes were discovered because they orbit normal stars in binary systems. The black hole's gravity affects the companion star's motion, causing it to wobble or orbit an invisible partner. By measuring the orbital parameters, astronomers can calculate the mass of the unseen object. If the mass exceeds roughly 3 solar masses, the upper limit for neutron stars, it must be a black hole. Additionally, if the black hole accretes material from the companion, the hot accretion disk emits X-rays that space telescopes can detect. This combination of orbital dynamics and X-ray emission has allowed the identification of dozens of black hole candidates in our galaxy. Given its enormous mass, Sagittarius A star is remarkably dim. It consumes material at a very low rate compared to its potential, accreting less than 1/1,000,000th of a solar mass per million years. This makes it a starving black hole, barely feeding despite being surrounded by stars and gas. The quiescence is thought to result from the specific conditions of gas in the galactic center, which is hot and diffuse, making it difficult to capture efficiently. When gas does fall in, it produces weak flares in X-rays and other wavelengths. Understanding why Sagittarius A star is so faint helps astronomers model accretion physics and the life cycles of supermassive black holes, which spend most of their existence dormant rather than actively feeding. Despite indirect evidence, confirmed intermediate mass black holes are rare. They're too massive to form from single stellar collapse and too small to be typical galactic nuclei. One possible formation mechanism involves the repeated merger of smaller black holes in dense star clusters. Another possibility is direct collapse of massive gas clouds in the early universe. Recent gravitational wave detections suggest some mergers involve black holes in the intermediate mass range, supporting their existence. Ultraluminous X-ray sources in nearby galaxies may also harbor intermediate mass black holes, as their brightness suggests masses in the hundreds to thousands of solar masses. Pinning down the population and formation mechanisms of these middleweight black holes remains an active area of research. General relativity places an upper limit on how fast a black hole can spin. If it rotated any faster, the event horizon would disappear, revealing a naked singularity which most physicists believe cannot exist. The maximum spin parameter is 1. Many observed black holes have spin parameters measured to be above 90% of this maximum, meaning they're spinning extremely rapidly. The fastest spinners likely formed from the mergers of two black holes, where the orbital angular momentum was efficiently converted into the final black hole's spin. Such rapid rotation affects the black hole's structure, shrinking the event horizon and expanding the ergosphere, and may play a crucial role in launching powerful jets. Though black holes themselves have no intrinsic magnetic field, the plasma in accretion disks is highly conductive and carries magnetic fields inward as it spirals toward the black hole. These fields become twisted and amplified by the disk's rotation and the black hole's spin. The resulting magnetic configuration can extract energy from the black hole and the disk, channeling material into jets that escape along the rotation axis. This process, described by mechanisms like the Blandford-Znaick process, converts rotational energy and accretion energy into the kinetic energy of jet particles. Understanding the interplay of gravity, magnetism, and plasma physics near black holes remains a frontier of theoretical and observational astrophysics. Quasars can be so luminous that they outshine all the stars in their host galaxies combined. The brightest known quasar, currently designated J0529-4351, shines with the light of about 500 trillion suns. Such extraordinary luminosity requires the central black hole to consume mass equivalent to the sun every single day. The energy comes from gravitational binding energy released as matter falls into the deep potential well of the supermassive black hole. At such rates, the accretion disk becomes so hot and dense that its radiation pressure can affect the surrounding galaxy, potentially regulating further star formation and black hole growth through feedback mechanisms. General relativity's equations allow for a mathematical solution called a white hole, which is essentially a black hole running backward in time. While a black hole has an event horizon you can enter but never leave, a white hole would have a horizon you can exit but never enter. Material would be expelled from the white hole's singularity, the reverse of matter falling into a black hole. However, white holes are purely theoretical and violate the second law of thermodynamics by decreasing entropy. No observational evidence for white holes exists, and most physicists consider them mathematical curiosities rather than real objects. They illustrate the symmetries and oddities of general relativity, but likely do not exist in nature. Science fiction frequently depicts wormholes as shortcuts through space, but the reality is far more complex. The Einstein-Rosen bridge solution to general relativity suggested a connection between two black holes, forming a tunnel through space-time. However, this bridge is non-traversable. It collapses too quickly for anything to pass through. Theoretical wormholes that could allow travel would require exotic matter with negative energy density to hold them open, something not known to exist in nature. While wormholes arise in the mathematics of general relativity, no observational evidence supports their existence, and quantum effects likely prevent them from being traversable even if they form. They remain speculative constructs, fascinating but unproven. Some solutions to Einstein's equations suggest that the singularity at a black hole's center could be a gateway to another region of space-time, possibly even another universe. These speculative ideas arise from extended mathematical models of black hole interiors. However, the singularity marks a breakdown in our current physical theories. Without a complete theory of quantum gravity, we cannot definitively describe what happens at the singularity or whether it connects to anything else. It's equally possible that the singularity is simply an endpoint, a physical boundary where matter ceases to exist in any recognizable form. Until we develop better theories, and potentially some way to probe black hole interiors, these questions remain in the realm of theoretical speculation. Physicist Roger Penrose proposed the cosmic censorship hypothesis, which conjectures that singularities cannot exist naked, exposed to the outside universe. Instead, they must always be cloaked by event horizons, preventing any observer from seeing the singularity directly. If true, this hypothesis would protect the predictability of general relativity by ensuring that the breakdown of physics at singularities doesn't affect the observable universe. However, cosmic censorship remains an unproven conjecture. Some solutions to Einstein's equations appear to allow naked singularities under special circumstances. Whether nature actually permits such objects, or whether some deeper principle prevents them, is still debated among physicists. Most researchers suspect cosmic censorship holds, but a rigorous proof has remained elusive for decades. When two black holes merge, the resulting black hole is initially distorted, not perfectly symmetric. It rings like a struck bell, settling into equilibrium through vibrations called quasi-normal modes. These modes depend only on the final black hole's mass and spin, making them a unique fingerprint. Gravitational waves emitted during this ring-down phase carry information about the black hole's properties. By analyzing the frequencies and decay rates of quasi-normal modes detected by LIGO and Virgo, scientists can test whether the merged object is indeed a black hole, as predicted by general relativity, or something else. So far, observations match predictions perfectly, providing strong confirmation of black hole physics. Individual stars can produce black holes up to perhaps 100 solar masses, possibly higher under special circumstances. But stellar evolution models suggest a gap in possible black hole masses, roughly between 65 and 135 solar masses, called the pair instability supernova gap. According to theory, stars in this mass range should explode completely, leaving no remnant. Yet gravitational wave detections have found black holes with masses that challenge this prediction. One explanation appears to be hierarchical mergers. Black holes that formed from earlier mergers can themselves merge, building up masses beyond what single stars can produce. These second-generation and possibly higher-generation black holes populate mass ranges otherwise inaccessible, revealing a new channel for black hole growth. When two galaxies collide and merge, their central supermassive black holes eventually sink to the center of the new galaxy through dynamical friction. They form a binary pair, orbiting each other while surrounded by stars and gas. As the black holes spiral together, they emit gravitational waves, eventually merging into a single, more massive black hole. This process is thought to be common in the universe's history, given how frequently galaxies merge. However, observing such binaries is challenging because the orbital periods are thousands to millions of years, and the final merger happens quickly. Pulsar timing arrays and future space-based gravitational wave detectors aim to detect the low-frequency waves from these cosmic collisions. After two supermassive black holes form a binary following a galaxy merger, they initially spiral together efficiently through interactions with surrounding stars and gas. But theoretical models suggest they might stall when separated by about 1 parsec, or roughly 3 light-years. At this distance, they've cleared out most nearby stars, reducing further dynamical friction. Without additional mechanisms, the final merger could take longer than the age of the universe. Various solutions have been proposed to explain how nature overcomes this problem. Interactions with a third black hole, a massive gas disk, or the black holes simply passing stars multiple times. Future observations of gravitational waves from supermassive black hole mergers would help confirm how nature solves this theoretical puzzle, though the exact mechanism remains actively debated. The no-hair theorem asserts that black holes are uniquely characterized by just 3 numbers. All other information about the infalling matter, its composition, structure, temperature, entropy, is lost. 2 black holes with identical mass, spin, and charge are completely indistinguishable, regardless of how they formed. This dramatic simplicity contrasts with ordinary objects, which carry complex information about their history and composition. The loss of information seems to violate quantum mechanics, which holds that information is never truly lost. This tension is at the heart of the information paradox and suggests that our understanding of black holes is incomplete, possibly requiring a theory of quantum gravity to fully resolve. General relativity describes gravity as the curvature of space-time and works beautifully on large scales. Quantum mechanics governs the behavior of particles and fields on microscopic scales and has been tested to extraordinary precision. But inside a black hole, at the singularity, both quantum effects and extreme gravity become important simultaneously. General relativity predicts infinite curvature, while quantum mechanics prohibits such infinities. This conflict signals that a more fundamental theory is needed. Candidates include string theory, loop quantum gravity, and other approaches to quantum gravity. A complete theory would resolve singularities, explain Hawking radiation from first principles, and perhaps solve the information paradox, unifying our understanding of the universe. One of the most counterintuitive aspects of black holes is that an infalling observer experiences nothing special at the event horizon. There's no signpost, no sudden jolt, nothing marking this point of no return. Locally, space-time appears smooth and uneventful. You would simply continue falling, perhaps not even realizing you've crossed the threshold. Only later, as you approach the singularity and tidal forces intensify, would the journey become fatal. From your perspective, the trip from event horizon to singularity for a stellar mass black hole takes less than 1,000th of a second, far too brief to appreciate what's happening. This smooth crossing is a consequence of the equivalence principle, which states that free fall is indistinguishable from floating in empty space. While an infalling observer crosses the event horizon in finite time, an outside observer sees something very different. Gravitational time dilation causes the infalling object to appear to slow down as it approaches the horizon. The light from the falling object becomes increasingly redshifted, stretched to longer wavelengths and dimmer. Eventually, the object appears to freeze at the horizon, its light fading exponentially. It never quite seems to cross, taking infinite time to reach the horizon from the external perspective. This apparent paradox arises because different observers measure time differently near black holes. Both perspectives are valid in their own reference frames, illustrating the relativity of simultaneity in curved space-time. The immense gravitational energy around black holes could, in principle, be harnessed. The Penrose mechanism describes how energy could be extracted from a rotating black hole's ergosphere. Matter thrown into the ergosphere could split, with part falling into the black hole and part escaping with more energy than it arrived with, effectively mining the black hole's rotational energy. Another proposal, the Blandford-Znaeck process, describes how electromagnetic fields in an accretion disk could extract rotational energy, converting it to power relativistic jets. While these remain theoretical possibilities with no practical implementation, they illustrate that black holes are not just destroyers, but also potential power sources, provided one could safely approach and utilize them. One powerful method for finding black holes relies on Newton's law of gravity and Kepler's laws of planetary motion. When a visible star orbits an unseen companion, careful measurements of the star's velocity and orbital period allow astronomers to calculate the companion's mass. If that mass exceeds the maximum for a neutron star, roughly 3 solar masses, the companion must be a black hole. This method has identified numerous stellar mass black holes in our galaxy. The technique requires precise spectroscopy to measure Doppler shifts in the visible star's light, revealing its orbital motion. Some systems show eclipses, providing additional constraints on the binary's geometry and the masses involved. Based on stellar evolution models and the rate of massive star formation throughout the Milky Way's history, astronomers estimate our galaxy hosts somewhere between 100 million and a billion stellar mass black holes. Most drift silently through space, invisible unless they happen to be in binary systems or pass near other objects. Occasionally, one might reveal itself through gravitational microlensing, briefly brightening a background star as it passes in front. This vast population of black holes makes up a significant component of the galaxy's unseen mass. They're the remnants of billions of years of stellar evolution, scattered throughout the galactic disk and halo, like seeds from ancient stars. These hidden objects represent the end state of countless massive stars that have lived and died since the galaxy first formed, creating an invisible population that far outnumbers the black holes we can actually detect. Understanding black holes requires solving Einstein's equations, which are notoriously difficult. While exact solutions exist for idealized cases, realistic scenarios like merging black holes require numerical simulations. Supercomputers break space-time into a grid and evolve the Einstein equations forward in time, calculating how the geometry changes. These simulations produce gravitational waveforms that can be compared with LIGO detections. They've revealed how merging black holes spin and orbit, how their event horizons merge into one, and how the final black hole settles down. Numerical relativity, as this field is called, has become indispensable for interpreting gravitational wave observations and understanding black hole dynamics. In the universe's first second, conditions were extraordinarily dense. Quantum fluctuations could have created regions dense enough to collapse directly into black holes without needing stars. These primordial black holes could have any mass, from microscopic to thousands of solar masses. Those smaller than about 10 to the 11th kilograms would have evaporated by now through Hawking radiation. Larger ones could still exist. Primordial black holes have been proposed as dark matter candidates, though observations have constrained this possibility. They could also seed the formation of supermassive black holes, providing a head start in the early universe. Searches for these ancient relics continue, seeking to determine whether they exist, and if so, how abundant they might be. Accretion disks around black holes reach such high temperatures that they radiate primarily in X-rays, which cannot penetrate Earth's atmosphere. Space-based X-ray observatories like Chandra, XMM Newton, and NewStar have mapped X-ray emission from black hole systems throughout the universe. The X-rays reveal the innermost regions of accretion disks, where matter spirals inward at relativistic speeds. By studying the spectrum and variability of X-rays, astronomers can measure the black hole's spin, the disk's temperature and density, and the presence of relativistic jets. X-ray observations complement gravitational wave and radio studies, building a comprehensive picture of how black holes accrete and release energy. In the famous images captured by the Event Horizon Telescope, the dark center is called the black hole's shadow. This shadow is actually larger than the event horizon itself. Light approaching the black hole is bent by gravity. Photons on certain trajectories can orbit the black hole multiple times before escaping or falling in. The photon sphere, at 1.5 times the Schwarzschild radius for non-rotating black holes, defines the innermost stable light orbit. The shadow encompasses both the event horizon and the capture zone, where light inevitably falls in. For M87 star, the event horizon is about 19 billion kilometers across, but the shadow spans 40 billion kilometers. This shadow is the silhouette that the Event Horizon Telescope imaged, surrounded by the bright ring of photons bent around the black hole. While LIGO detects gravitational waves from stellar mass black holes, supermassive black hole mergers produce waves at much lower frequencies, outside LIGO's sensitive range. The Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s, will detect these low-frequency waves from space. LISA consists of 3 spacecraft in a triangular formation, separated by 2.5 million kilometers, flying in an Earth-trailing orbit. It will detect the mergers of black holes ranging from thousands to millions of solar masses, events that occur when galaxies merge. LISA will also detect signals from extreme mass ratio in spirals, where stellar mass black holes spiral into supermassive ones. These observations will revolutionize our understanding of black hole demographics and galaxy evolution. Near a black hole, gravity reaches strengths unattainable anywhere else in the accessible universe. Space-time curvature becomes extreme. Velocities approach light speed, and time dilation becomes dramatic. These conditions provide stringent tests of general relativity. So far, every prediction has been confirmed. Gravitational wave signals from merging black holes match the theoretical waveforms precisely. The images of black hole shadows agree with calculations based on Einstein's equations. Measurements of time dilation and orbital dynamics near Sagittarius A star conform to relativistic predictions. Any deviation would signal new physics beyond general relativity. But Einstein's century-old theory continues to pass every test with flying colors, even in the universe's most extreme environments. In the far future, according to current cosmological models, long after stars have burned out and galaxies have faded, black holes may be the last structures remaining. Over timescales of 10 to the 100 power years, even supermassive black holes would evaporate through Hawking radiation, if Hawking's theoretical predictions hold true. After they're gone, the universe may contain only dilute radiation, cooling asymptotically toward absolute zero. This scenario represents one possible outcome based on our current understanding. Alternatively, some theories propose that black holes could be connected to new universes or cycles of cosmic evolution. The relationship between black holes, entropy, and the arrow of time hints at deep connections between gravity, thermodynamics, and cosmology. Understanding the ultimate fate of black holes may prove key to understanding the ultimate fate of everything. Researching black holes has driven innovations in many fields. Gravitational wave detection required advances in laser technology, vibration isolation, and data analysis algorithms. The Event Horizon Telescope pushed the boundaries of radio interferometry, data storage, and synchronization across continents. Simulating black holes demands cutting-edge supercomputing and numerical methods. These technologies find applications beyond astronomy, including precision manufacturing, communication networks, and medical imaging. Additionally, theoretical work on black hole thermodynamics and quantum gravity has deepened our understanding of fundamental physics, influencing fields from particle physics to quantum information theory. Black holes, despite being distant and seemingly irrelevant to daily life, have inspired practical benefits through the research they've motivated. Common sense breaks down near black holes. Time is no longer absolute, but depends on gravity and motion. Space can be so curved that inside the event horizon, the future direction in time points inward. The usual notion of causality, that cause precedes effect, becomes murky. An observer watching matter fall into a black hole sees it freeze at the horizon, never quite entering, while the falling observer experiences crossing the horizon and reaching the singularity in finite time. Both perspectives are correct within their reference frames. These paradoxes are not flaws, but features of a relativistic universe. Black holes force us to abandon Newtonian intuitions and embrace a cosmos governed by relativity's strange but beautiful rules. The information paradox remains one of the deepest puzzles in theoretical physics. If a book falls into a black hole, is the information contained in the book destroyed when the black hole eventually evaporates? Or is it somehow preserved? Recent theoretical developments suggest information might be encoded in subtle correlations in the Hawking radiation, requiring entanglement between early and late radiation. Other proposals involve modifications to the event horizon structure or quantum corrections to general relativity. Some physicists propose that remnants might persist after evaporation, carrying information. The debate touches fundamental questions about quantum mechanics, gravity, and the nature of information itself. Resolving it likely requires breakthroughs in quantum gravity that we have yet to achieve. A sufficiently advanced civilization might, in principle, harness a black hole as an energy source. Material falling into a black hole releases tremendous energy, which could theoretically be collected from the accretion disk's radiation. The Penrose mechanism, a theoretical process, describes how energy could be extracted from a rotating black hole's ergosphere. Matter thrown into the ergosphere could split, with part falling into the black hole and part escaping with more energy than it arrived with. Another theoretical proposal, the Blandford-Znaeck process, describes how electromagnetic fields in an accretion disk could extract rotational energy. While these concepts are consistent with known physics, they remain theoretical with no practical implementation. They illustrate that black holes are not just destroyers, but also potential power sources, provided one could somehow safely approach and utilize them. A century ago, black holes were barely conceived, existing only as strange solutions to newly formulated equations. Einstein doubted they could form naturally. Today, they're established astrophysical objects. We've detected hundreds through gravitational waves, imaged their shadows, and measured their properties. We understand how they form, how they grow, and how they influence galaxies. Yet mysteries remain. The nature of singularities, the information paradox, the formation of supermassive black holes, all these questions beckon further research. Black holes stand at the intersection of our grandest theories, quantum mechanics and general relativity, challenging us to unify them. The next century may bring even more profound discoveries. Few phenomena capture the imagination like black holes. They're simultaneously simple and complex, destructive yet creative, invisible yet detectable. They warp space and time, swallow light, and challenge the limits of science. Every discovery raises new questions. Every answer reveals deeper mysteries. Black holes embody the best of scientific inquiry. They demand rigor, inspire awe, and reward curiosity. They show that the universe is stranger and more beautiful than we can imagine. Whether you're a professional physicist or simply someone gazing at the night sky, black holes offer a reminder that the cosmos is vast, full of wonders yet to be explored. Black hole physics draws on general relativity, quantum field theory, thermodynamics, information theory, and more. The study of black hole entropy inspired holographic principles, suggesting that the information in a volume of space can be encoded on its boundary. Connections to string theory have led to microscopic models of black holes as quantum states. Black hole thermodynamics influenced understanding of entropy and the arrow of time. Even pure mathematics has benefited, with solutions to Einstein's equations inspiring new geometric methods. This interconnectedness illustrates how fundamental physics forms a unified whole. Black holes, sitting at the nexus of multiple disciplines, exemplify the deep connections underlying our description of nature. No two black holes are exactly alike in detail, yet any black hole is fully characterized by its mass, spin, and charge. This paradoxical combination of uniqueness and simplicity is remarkable. A black hole formed from the collapse of a hydrogen star is identical to one formed from iron, provided the mass, spin, and charge match. This universality makes black holes the simplest macroscopic objects in the universe, far simpler than stars, planets, or even atoms, which have internal structure and composition. The no-hair theorem captures this elegance. Black holes shed all complexity, leaving only these three numbers. It's a profound statement about how information is lost and how gravity organizes matter. The era of black hole astronomy is just beginning. Gravitational wave detectors are being upgraded, increasing their sensitivity. The Event Horizon Telescope continues expanding, adding more telescopes for higher resolution. Future space missions like LISA will open new observational windows. Astronomers will detect more black holes, observe them in more detail, and discover new behaviors. Theoretical work will progress, perhaps finally resolving the information paradox or unifying quantum mechanics and gravity. Each generation builds on the last, expanding knowledge and raising new questions. The study of black holes exemplifies science as an ongoing journey, never complete, but always advancing, driven by curiosity and the desire to understand the universe. When we study black holes, we're exploring the fundamental laws governing existence. We're asking what space and time are, how gravity shapes the cosmos, what happens at the boundaries of knowledge. These questions connect to who we are as conscious beings in a vast universe. Black holes challenge us to think deeply, to question assumptions, to embrace mystery. They remind us that there's always more to discover, more to understand. In reaching outward to the most extreme objects in the cosmos, we reach inward, confronting the limits of our understanding and expanding them. The quest to comprehend black holes is part of humanity's greater quest to comprehend reality itself. And so, as we close this journey through 100 facts about black holes, let yourself rest in the quiet wonder of what you've heard. The universe continues its slow dance. Black holes spinning silently in the dark, stars orbiting, galaxies merging. Time passes differently near those distant horizons, but here, now, your time is for rest. The mysteries remain, patient and eternal. And in the morning, the world will still be full of questions waiting to be asked, wonders waiting to be discovered. But for now, all you need to do is breathe, slowly, deeply. Let the weight of the cosmos settle gently around you. Let the pull of sleep, gentler than any black hole's gravity, guide you into rest. Thank you for listening. If you enjoyed this journey through the universe, please consider liking this video, subscribing to the channel, and sharing your thoughts in the comments below. Your support helps these cosmic explorations reach others who, like you, find peace in the wonders of the universe. Good night and sleep well.